motivation why I started this project. So there are these automation systems out there. They are at universities, at research institutes. These are just assembly lines, like in the industry where cars are assembled or notebooks are assembled. But it's just models. They're just small, so small scale assembly lines, which do not really assemble something, but they are used for education, for research, and they are, for example, sort things by color or by size. And they are produced, for example, by Festo, like this one. And currently they are controlled by proprietary PLCs, usually soft PLCs. That means for each of these, for each small of these blocks, there is a Windows PC standing and connected to an I/O interface over USB, and then there is a proprietary software controlling these devices. And there are some issues with the current solution. They are slow. They have very high latencies, so they react very slow. So they have to run very slow to have enough time to react. And they are unreliable. They are, of course, closed source. They are always required as Windows PC. So for every of these blocks, you need a Windows PC and a desktop PC. So it is, of course, very expensive. The PC is expensive, and the I/O interface is expensive. It's just a small box, which are connected over USB and offers 24-volt interface, inputs and outputs, and costs around €400. So the idea is to replace these interfaces. And the goal of the project is to develop an open source PLC based on the Raspberry Pi, so to replace the current ones. It should be faster, it should be more reliable, it should be open source. That means the software should be open source and the hardware should be open source. It should be standalone, so it should not require a Windows PC, and it should be a little bit cheaper than the original ones. So the model I'm currently working on is the 24D1. It consists of two components. On the back side, there's the Raspberry Pi model B+. I think most of you know the Raspberry Pi. It's just a small computer running a Linux distribution, in this case running Raspbian. So it offers USB ports, it offers an Ethernet interface, an analog audio-video output, an HDMI output, and a 5-volt power supply connection. And here on the other side, it offers general purpose I/O pins. And to these pins, I connect a board which I especially designed for this project, which just takes the input. So the complete logic is running on the Raspberry Pi, and it takes the input from the Raspberry Pi and offers 24-volt interface. So it has digital outputs. It has per port 8 digital outputs and 8 digital inputs. And there are a lot of LEDs here. Here are LEDs for the inputs. So the green LEDs, they are on if there are 24 volt applied to the input pin, and there are LEDs for the outputs. They are green if there are 24 volt. If it's by the Raspberry, it's set to hide the output, so there are 24 volt on the output. And there are also red LEDs that indicate that there is a miswiring or that you apply 24 volts to an output. So the goal is to make it very safe, because it's operated by students, by researchers who never will read the manual. So it has to be almost indestructible. So if there's any kind of miswiring, it has to indicate that and must not be destroyed. So that's not a problem. There are freewheeling diodes on the outputs. There's short circuit protection. There are Schmidt triggers to suppress any noise on the inputs. So that's everything not a problem. I produced a prototype. It looks like this. later show it on in action. So here on the back side, there is the interface from the Raspberry, and in the front there are the 2 ports for the automation system. Here are the LEDs for the outputs, for the errors. Here are 2 LEDs for that 24-volt power supply is connected, and here are the inputs. So everything's working fine. I can control the automation systems, but there is one really big issue. As long as I do not touch it, it runs very nice. But the problem is, it is normally running floating. So it's connected to a 5-volt USB power supply, which is not connected to Earth ground. It's floating. So the problem is, when I know while it's running, connecting Ethernet cable or an HDMI cable, which is on the other side connected to ground, then there will be something like an electrostatical discharge. It's very small, but it is sufficient to lose the completely internal state of this device. So the outputs will randomly switch. The inputs, the I/O expanders on the bottom, they will just restart. And yeah, here there are latches for multiplexing the outputs, and they just lose their state. So the Raspberry Pi itself is not affected by this problem. So I make a test circuit. I just take a latch. So it's a normal latch, that a transparent latch. So it means everything that's on the input will be propagated to the output if the latch enable is high. If it's low, then it will just ignore any inputs and just just keep the outputs that are was last time set. And the output enable is inverting, so it means if it's low, then the outputs are really driven. Otherwise, they are 3-state, so they're not driven. And then I have a 5-volt power supply, maybe a USB power supply or even a battery. Then I have a 100 nanofarad decoupling capacitor, and on each output I have a resistor in series with a LED diode. So if the LEDs are initially off, then obviously it should stay forever off. Yes, there is on each input it's low and the latch enable is low. So obviously nothing should change. The problem is, if I connect to any point, a ground, a really earth ground, to any point of this ground here, then they just do random things. Let's turn on, turn off. I have the breadboard here, I can show it later on. So if I hear at any point I connect it to earth, random things happen. And the problem is I have absolutely no idea what to do. I talked with a lot of people, a lot of students who study electrical engineering and informatics, physics, whatever.
So don't connect it to ground.
That's unfortunately not an option.
You have developed a detector if it is connected to ground.
Yeah, I also talked to a lot of people who really experienced, who really built hardware, and the reaction was always the same. They looked at me and said, "That's a strange problem. I never saw that before. No idea what to do." So my hope is that anybody of you had any idea, maybe seen this problem before, had any idea what to do.
Yeah, well, at least for physics, if you have you get a short pulse of something, and you don't have any inductivity. So whenever you want to work around short pulse and things like it, you have an inductivity in your power range. So having both in plus and minus to your thing, some inductivity might help. So that's what you always do. Not being an analog electrician at all. So the capacity doesn't help for short things. It's only for leveraging low frequency. But if you get a high frequency pulse, the capacity it's always passing high frequencies. That's not what you're looking for.
Yeah, okay, I read that a normal solution for such problems would be to separate the case ground from the circuit ground, so that it's not possible to apply earth ground to this here. But the problem is the Raspberry Pi has these USB connectors, Ethernet connectors, and HDMI connector, and they're directly connected to the ground of the Raspberry. So I cannot isolate these connectors. I cannot isolate the case from the circuit ground. And I mean, the Raspberry is not affected by the problem, so it should be possible to achieve that without separating the grounds. But I just don't know how. So.
Two things I know is the Z-diodes, that you limit at least the voltage level if it's getting higher than 5 volts, or your VDD 3.3 volt, whatever, that you're clamping whatever is getting higher and maybe even destroying your things. And the other is really having inductivities in the power supply, because that's blocking all the sparks. having inductivity
So you
both in
mean
the ground line and the plus line really helps for some of
So you
these
mean
issues.
inductivity here in this power supply?
Yeah,
you can-
V1 plus and V1 ground.
Yeah, between this V1.
You have to do it in both
Plus
lines, not only for the power supply, but only also for the, somewhere in the
And the
ground line.
line.
Okay.
Too small inductivity.
Yeah, of course, I have an inductivity between this minus of the power supply and between this, of course. But I cannot include an inductivity between the Earth and this point. So if I connect the Earth to the case, I cannot put an inductivity between. That's my problem.
If the Earth comes from your Ethernet connector, you can put in inductivity between the Ethernet connector and the rest of the board.
Yeah, but the Ethernet connector is directly connected to the ground on the Raspberry Pi.
Yeah, but you mentioned that Raspberry Pi isn't infected, so you can put it between your board and the Raspberry Pi.
That would be possible. That would be possible, but it would be better to find out why the Raspberry is not affected, and to make.
Oh, you want
it
that the Raspberry is also affected?
Yeah,
I guess they have the same things. They will have some counter measurements with lots of inductivities, but not capacities in that case, I would say. That's for
Yeah,
keeping
but,
it not oscillating and low frequency.
there are no inductivity on the Raspberry Pi. So the circuit is published, and there are no inductivity between the to ground between the connectors. They're just directly connected. Okay, so there's also a website, RPiPLC. So if you want more information or want to look at the circuit diagram, it's published. You can look at it. If you have any questions or suggestions, you can talk to me. I will be very happy to get some ideas. So thank you for listening.